to acknowledge this first. Okay. Hope you can still see it. I tried to switch to the full screen.
Yes, it looks perfect. Okay, so we are very pleased to have Professor Tanja Horn here today to speak with us about the structure of pions and kaons and experimental illumination of the internal structure of these mesons at GeLab and also at the future EIC. Tanja, whenever you're ready.
Great, yeah, thank you very much, Jennifer, and the entire team at Berkeley for this invitation. And of course, I must say we had just a second snowstorm in DC, so I probably would much rather be on the West Coast now, but anyway. Okay, so so I will speak about the intrigues and mysteries and interesting prospects for accessing the Pion and kaon structure, and of course a little bit today also about the global picture, essentially how these relate to our understanding of hadron mass. And mostly I will, as said here in the title, I will focus on experimental access. I'm an experimentalist, so that will be the main focus. But of course there will be some references to theoretical treatments you might consult. And I know, of course, some people here on the call are, of course, very much involved in these discussions. Anyway, okay, so here's the outline. First, I will speak to accessing observables related to the Pion and kaon structure, in particular here, the elastic meson form factors, through the Sullivan process. There's some details one has to consider and actually has to show that this is a valid technique to do that. And then say a little bit about the status. So in particular, say where we are, for instance, with measurements at the Jefferson Lab to measure these form factors for the charged pion and charged kaon, up to a reasonable range in Q squared. Then I will also say how we access the meson structure through the TDIS experiments. So that would be the Pion and kaon structure functions. And then also talk about opportunities at the EIC, and that will be for both for the meson form factors and also for the structure functions. So if you start maybe here, just taking a kind of a brief overview look, and most of us, of course, familiar with this, is that essentially the mass of hadrons is mainly given, or 99% given by the dynamics. So basically, we say here the light quarks acquire most of their masses as the effect of the gluon cloud. And we can look at the quark mass functions here in the left-hand side. I hope you see my cursor, by the way. One can see here this mass acquisition function as a function of momentum, and one can see the light quarks. Essentially here, as you see, this dependency on momentum acquire essentially all the masses. All the mass of the quarks is acquired by this dynamical process. Of course, here you see the top, the bottom and charm quarks, or the heavier quarks, essentially. So here, basically, the Higgs mechanism is the prevalent dominant mechanism. And then we have in between strange quarks, which kind of follow this green dashed line. So essentially, we have two mass-generating mechanisms in the standard model of particle physics. So one is related to the Higgs boson, as I just mentioned, the top two lines, and then the other one is embedded in QCD, and it's basically strong. If you like the QCD model, a strong interaction piece, if you like to call it maybe this way, and that gives you this behavior as shown here. And that's responsible for the basically this mass, this emergent mass that characterizes the protons. So at this 1 GeV scale, as shown down here, and it's in this way also basically the mass of all observable visible matter. Now, of course, the source and the impact of this emergent mass is quite interesting to understand, and remains puzzling. And one example is shown here. So, for instance, we see here the mass of the proton is 1 GeV on that scale. Most of this is here says acquired by the dynamical chiral symmetry breaking. But then you have the mass of the kaon and pion being about half a GeV and being 0.14 GeV. And that's puzzling because if you see here, again, the quark mass functions, they should be universal. So basically, we should be treated the same way, independent of if it's a proton, kaon, or pion. But yet you see these large differences in masses of these hadrons. So let us then continue and say a little bit more about the origin of mass in particular in the light mesons. They're quite interesting here. It's actually unique to study a little bit the mass about them because, of course, what they are essentially the lightest bound states, quark systems, with a relatively simple valence structure, and they're also would be, or perhaps even the Nambu-Goldstone boson themselves. We can exactly write from QCD the mass functions as shown down, over here. In terms of the current quark masses, there's basically a very clear prescription to do that. But if you do this for these exact statements, you can see in the mass follows increases as square root of m, if you like, with the mass of the constituents. You see there's a sharp contrast with models like the constituent quark model, where the bound state mass actually would rise linearly with constituent mass. And that would mean that with this model, that the mass of the quarks in a nucleon would be about 300 MeV, in a pion would be 70 MeV, and the kaon would be 200 MeV. But clearly that is not real. So it's basically shown, or can be shown, that the mass functions of these quarks should be the same, regardless of which hadron the quarks reside in. And so it is, the mechanism would be the, as I already mentioned, dynamical chiral symmetry breaking that gives these pions and kaons masses and relatively light masses. So as I said, again, it is quite important to understand the source and impacts of the dynamic generation of the hadron mass, and in particular, the pions and kaons allow us to kind of have a window and look into the masses of hadrons. So then let me turn, after this very brief kind of introduction, I come back to a little bit later when I talk in the context of the ERC about it. But let me first review a little bit the process experimentally. So what we're using is, we have two mechanisms, broad mechanisms available to us. One is the Sullivan process, where one scatters, hard scatters from a virtual meson cloud in a nucleon. And the other one is the converse of it, the inverse of it is the GeV process, where one annihilates with the anti-quark. I will focus here actually only on the Sullivan process with the two reaction channels. One of them, as I mentioned, is the elastic electromagnetic form factors. That's the first one I will focus on. And this one will give us information how this emergent mass, as I discussed in QCD, manifests in a wave function. And then later I'll talk a little bit more about the structure functions and PDFs associated with them, which gives us the information about quark-gluon momentum fractions. So both of them dynamical, aspects that relate directly or give us shed some light on the origin of the mass of hadrons. As I mentioned, with the Sullivan process, and if you again look at this diagram up here, that we look at, so if the virtual photon scattering from the meson cloud, from the meson cloud of the proton, and emitting the pion right here. Using this process or this reaction channel has some caveats. In particular, because if you heard already or kind of paid attention here, you heard that I basically said I'm talking about the virtual meson cloud. So what one really has to show here is that one can use this virtual meson cloud of the proton as a real pion target, which of course a real pion target doesn't exist any other way. So that's really the only way we can do it. And to do that, we typically take data as a function of some kinematical variable, and in this case, it's one that's associated with t, so that we can monitor if this process becomes space-like, if this pole is essentially, this pole process which characterizes this reaction channel is associated with the ground state meson. Basically, in short, one would say, if that's the case, if the pole down process is dominant, we can call this virtual pion a real pion, and we can go ahead and use it as a target. So to do this, to check this condition, and that's of course the first step and very important, we can take data as a function of t, as shown in this diagram here, and cover a full range or as wide as possible range in t, and compare with a phenomenological and theoretical expectation that extrapolate to the on-shell point. And again, if this agrees, then one can go ahead with the experimental extraction, which of course has to be done with a careful analysis as well. Now, to give some indication where one should look for this extent in t, where one should in particular take data around, that's in theoretical calculation to be found, t of 0.6 approximately. So this range in t would go up to 0.6 for pions and to 0.9 GeV squared for the kaons. And in this regime, the kaon or pion structure would evolve slowly, and then so this condition that's summarized up here is satisfied, and we can proceed and use the well-constrained experimental analysis to extract the meson structure. Now, most progress of this has been done with the elastic form factors. The experimental validation, in particular at GeV JLab, has been a major focus topic. So I will talk about that first. And then, as I said, later come to the pion structure and kaon structure functions. So as I already said, the meson form factors are of special interest in hadron structure. They're in fact, the probably the most straightforward and easiest way to study a QCD quark system. I mean, the Pion is the lightest QCD quark system, and also, as already mentioned, has a central role in our understanding of the dynamic generation of mass. And so it's the clearest test case in that already has been shown over decades to study the transition from non-perturbative to perturbative regions. And the kaon, of course, is the next simple system that also contains a strange quark. There's been a lot of advances with these measurements over the last decades, and I'll say a few more words about that one. And one can also show that this form factor can be, in fact, or is related, in fact, to the distribution, or rather linked to the distribution function, which is, of course, a probabilistic interpretation of the Pion-KAON structure, which is kind of shown again here. This is a mass function for two different degrees of dynamical chiral symmetry breaking. So we have the blue dashed line here and the green line, again, two different degrees of this. And then shown below here is a calculation with these distribution functions, which feature, of course, in the extraction of the form factor. Distribution amplitudes are used, obviously, in the calculation for calculating the form factors. And we see that as a clear visible difference. Here, again, the blue dashed line corresponds to this one up here, and the blue solid line, the green solid line corresponds to the top one. So one can see there's a clear difference. And by measuring the observable, the Pion form factor, in this case, one can essentially observe the impact, and again, shed light on the dynamical chiral symmetry breaking, the degree of it in the meson wave function. So again, very important to measure these observables, and we are fortunate that we can access them at facilities like the Jefferson Lab and also the EIC. So just a few words about the progression of data taking, in particular also related here to extracting the meson form factors and measuring Pion structure and kaon structure function. So this is an activity that has been ongoing for many, many decades, so starting as early as 1959. Typically, the way it looked like is that there's been a major progress, a breakthrough in theory. Then there's an array of facilities built, as you see here, that take excellent amount of data and address and validate theories and so on. Same here with GeV JLab. And now one could say that we are basically profiting from, again, major progresses on hadron structure studies in theory. And linked to that, also the new experimental facilities, new and upgrade experimental facilities that become and will be becoming available to make these measurements. And these include, but are not limited to, of course, the Jefferson Lab and EIC. There's also Compass, obviously, and there's a facility in China that will make similar measurements. So it's a great opportunity that we have currently and in the next few decades for making these measurements and shedding light on meson structure. Okay, so let me then talk first about the Pion form factor that we're measuring at the Jefferson Lab. Mainly, it's of course not the first time measured there. It has been measured at CERN early on already, in particular there through Pion electron scattering. That's a direct measurement of the Pion form factor, but due to kinematical factors, it's limited to a relatively low Q-squared. So you see the data up here, or down here rather, elastic scattering data that are limited to a Q-squared value of about 0.25. So if you remember from my earlier slides, of course, we want to measure up to a Q-squared value of about 10. So that's really rather limited at low Q-squared, low energies, low momentum transfers. These data are nevertheless very important, of course, because they helped us to constrain the Pion charge radius. And so the value, accepted value is shown here. And just to give you an idea, like why are we limited in Q-squared? Well, it's just because in this measurement, basically the Q-squared value you want to achieve is proportional to the Pion beam energy. And so if you wanted to go to 1 GeV squared, you would need something like 1,000 GeV Pion beam, and you can do the math. I mean, it's just not very efficient to do it this way. And of course, everything at these energies is scattered very forward and makes it experimentally extremely challenging and simply not very profitable. So instead, one uses this process, and this we're going back to the Salvin process I talked to you about. When you recognize some of the words, it just simply says we are measuring indirectly using the Pion cloud of the proton, using the Pion electroproduction process. Here in this the picture also indicate, by the way, the value of T as the momentum transfer to the nucleon. So that's the same as the value, of course, the Mandelstam observable variable that I talked to you about earlier. So then if we, again, have the conditions satisfied, I talked about this earlier, pion pull process dominates. So basically we can say virtual pion target is real pion target, so we actually have a pion target. Then we can extract essentially the form factor by measuring a cross-section. This is a very typical thing. Of course, we're measuring a cross-section in experiment and then extracting the observable from this cross-section measurement. In this case, modulo the coupling factor, as you see here, the pull process, and q squared just for scaling purposes. Of course, this is very simplified. In practice, we use a much more sophisticated model, and I would refer you to our publications for that. But here, just as a summary, the main requirements for these experimental processes. So what you need to do a so-called longitudinal transfer separation of the cross-section. But that's important because as you see in this equation here, we need the longitudinal cross-section. So we need to isolate this part. We need to make sure we select the pion pull process. That's just making sure we're using basically the Salgon process, as I said earlier. And then we extract a form factor, and here I specify using a model. So it's not as simple as this one, it's actually using a model. And then, of course, we have to, in the end, validate the technique, basically doing model-dependent checks. So that was in a nutshell how this works. Just one slide, again, for people interested, what LT separation is. Essentially, you're measuring at two different beam energies that are indicated here. Here's a cross-section of the pion, as mentioned earlier. By the way, here's the unpolarized cross-section listed in this relatively simple equation. So you measure as a function of the azimuthal angle at two different energies indicated by red and by blue. And that you keep in mind here because we need one high energy, one low energy. I will come back to this in a little bit. And you measure this at fixed values, kinematic values of q squared w and t, and then fit this form of the equation to the data and extract from it the coefficients, which then correspond to the longitudinal cross-section, which will give us the form factor, and the transverse cross-section and two interference terms. So that can be done too. It looks simple and trivial to do this, but it's, of course, as usual, experimentally, it's not. The systematic uncertainties play an important role, and in particular, due to this factor epsilon, because it comes in amplified in the extraction of the longitudinal cross-section. So experimentalists know what that means. It typically means you have to really control spectrometer acceptances, kinematics, efficiencies, and what have you. And for an experimentalist, really the only device that is useful to do that would be a magnetic spectrometer, where you can make a precision cross-section measurement. And this we do at Jefferson Lab in the Hall C. So that's one of the major strengths of Jefferson Lab to make these precision cross-section measurements. So, so now if we have the cross-section, the longitudinal cross-section, if we have confirmed we can isolate it, then of course we still need to check if we can, really have the full process that we're looking at. We have to check model-dependent uncertainties, as I mentioned. We have been doing this over the last decade, actually it's now 2 decades, that have given us really the confidence that we understand how the electroproduction method works and yields the physical form factor. Now the way we do it, I'm just showing here 2 examples, is to take data, and if you remember this from my earlier slide, we take data as a function of t, as a function of the variable that's of course of interest for the extraction, and check if the form factor is the same at all values of t. If it's the same at small t, which is close to the physical pole, then the same as at large t, then of course we can be confident and say that for one, of course, well, obviously the values do not depend on t. And more importantly, it gives us the confidence that our model is applicable in the kinematic regime of the data. So that's the model dependence. Another point was the pion pull diagram. This we can do by taking the ratio here of the longitudinal cross-section for both pi minus pi plus production. So in reality, you're looking at the amplitudes essentially. And there's a prediction for that it should essentially come out at unity if the background processes are negligible, or in other words, if the pion pull diagram is dominant. And as you see here, the data show us over the last decade show us they are. And so we are confident that the method we are using is valid, and we actually do extract the physical pion form factor. Here, just a very brief description. This is how Jefferson Lab looks like. These are some magnetic spectrometers look like. They look like the giant microscopes, essentially. They're used in an optic system consisting of magnets and detector packages in these shielded electronics huts to collect the data. There's also dedicated PID systems. My group built one of them. It's an aerogel Cherenkov detector, as you see right here. I'm not spending too much time. I just wanted to kind of flash the current status. So this is an experiment. It's called PION LT, which measures, has its goal measuring the pion form factor, and in particular measuring LT separated cross sections which then also allows for studies of the scaling or QCD factorization for GPD extractions. But here I'm focusing on the form factor, so I'm just showing you here essentially the projections for the data that are being taken right now and later this year. And you see the projections here in the light blue for this experiment, and also this red data point at up to Q squared of 8.5. So up to about 10, we should have good data. And here's just, you see, it's an ongoing experiment. So you see some settings are done and some are still coming. And if you remember what I said earlier, we need both. We need data at a lower energy and a higher energy called epsilon here. Otherwise, you can, of course, not do a full extraction and an actual extraction of the form factor. We also have data, as I see here, from another experiment we completed in the last 3 years, which will give additional points that are shown here in red. But I'm not going to spend much more time. I'm just giving you here the range of possible range of extracting the form factors at Jefferson Lab from these running experiments. There's, of course, the question if that's enough. But as I said, GeLab will push the Q-squared reach quite a bit. There's still some key questions that regard the emergent mass, hadronic mass, that we cannot quite answer there. In particular, we would need data even beyond 10 GeV, as it says here. And for this, one needs a different machine, and that would be the Electron-Ion Collider. And I'll talk more about that a little bit later, because first I'd like to focus here on the other process I mentioned already earlier, basically the measurement here of the structure functions and PDFs extractions from the data, which give us information about the quark-gluon momentum fractions. So here again, we're using the Sullivan process. In this case, we are detecting a scattered electron. We actually don't detect now the pion. This is the pion target. It's the same thing, of course. I mean, you still have to show that it's a valid pion target, but we will not detect it here. But we do tag the outgoing target nucleon, which for the pion case is, of course, the neutron. So if we look at the current status, at the currently available data, they're essentially data from PION JLab, from Fermilab and CERN, is shown here. And then from the DIS, from the Sullivan process, as the one that I'm looking at here, from Hera, so basically H1 and Zeus, and you see them summarized here. And the main conclusion I'd like you to get from this slide, in particular, if you're familiar with the data on the proton, is that there's essentially not much data for pions at all. And if you go to kaons, basically it's consistent with nothing. So just a few points. If you remember, again, we had to validate that actually this pion target is a real pion target that we can use. So at Hera, there's various studies have been done. In particular, what you see here in this plot is data from Zeus taken, where basically the studies were similar to what I mentioned, what we do for the pion, where you look at the dominance of the isovector process of an isoscalar process, which in this case could be sort of considered like a background. And what one sees is that the neutron events isovector, so basically it means that the charged pions in this case, again, pions is what we're interested in, pion is the target for us for this particular process, is dominant. And so it means that one can in fact use the one pion exchange mechanism. It's a dominant mechanism. We can move forward and extract the pion structure function from these data. There's of course more to be checked and will have to be continued to be checked. In the same detail as for the pion form factor, that the Sullivan process is the right process in the considered kinematic range to use to extract this information. And of course, also not to forget, in practice, one uses in-depth model and kinematic studies to include, for instance, rescattering and absorption. But here you see just in this graph here, I showed it to you on the previous page, is the data from H1, for instance, where these pion structure functions were actually extracted from the data set after checking for the validation of the Sullivan process. Okay, so if we then go on, there's, of course, if you noticed here already, if I go one more time back for a second, that the coverage is mostly around rather small values of x. So we're going to around 10 to the minus 3 or so. Now, there's many of us here are probably familiar with the challenges and the mysteries, rather, of the large x structure of the pion. In particular here, the tensions, or rather the apparent inconsistency between models and data, between data and so on. And there were, of course, many questions about that ongoing. So for instance, here, if you look at PDFs were going maybe as 1 minus x pi, which of course differs from the perturbative QCD prediction, which should go as 2, which of course, again, there's this additional considerations where perhaps this structure is even too restrictive. Perhaps it should be a little bit different still. So there's various considerations of this. There's also was addressed problems with data analysis. So many things were considered here, but next leading order fits, improved proton PDFs, CQuark contributions, and more flexible extractions of the PDFs, which kind of relates to what I just said. There's also a very important discussion about the next leading order gluon resummation effects on the theory side. And you see here essentially a summary of the most recent analyses. And all of this at the large Q squared, basically the experiments at GeLab can provide important input, and I'll show how the data will come in a little bit. First, just here's an overview of the experiment. Since I also showed the Hall C experiment, this is the so-called Hall A at GeLab. If you're familiar with the Jefferson Lab, has 4 experimental halls. I talked about one already for precision measurements of the form factors and cross sections. This is one other hall, Hall A, which also has magnetic spectrometers and also capabilities of installing large equipment and various other configurations. This is will be using one of them. So it's using basically proton tag detection with a GEM-based MTPC at the pivot. The arrow shows here, it will go here. And the electron beam, of course, will go in this way and allow for high luminosity measurements, which of course is important here, plus a large acceptance, because what we're talking about are processes with relatively small cross sections. So this will go on there. And then here, as promised, I'm showing you the projections where these data will be taken into their projected uncertainties compared to the world data. You see here in red the prospect for the Pion measurement. And then here on the right, the one for the kaon measurement, which will also be done. For the kaon, I should point out in particular, you see, of course, here only the curves, and that's just because there's essentially no data. So this will certainly be a very important measurement, a pilot measurement, if you like, exploratory measurement for the kaon, and of course, give us a lot of guidance moving forward. Okay, so here I'm just taking a breath and so on, and now I gave you the overview and status of data available at Jefferson Lab and beyond, before, let's say. And now in time, let us move a little bit forward and say what can the ERC do, in particular here for meson structure measurements, structure functions, and meson form factors. Here, for people who have not seen it, of course, before, this is just a schematic of the ERC as it will be built at Brookhaven National Lab. And the energy is available for electrons and protons, and also for ions. In this case, what is most important is that these measurements will have a great acceptance for these type of forward physics measurements, and the low momentum nucleons will be easier to measure. Just here's an example, I'm using this as an example here. It's an acceptance for ERC shown versus the one at Hera. So remember, I showed you earlier the data from Zeus. And essentially what you can take away from this is that the acceptance for these events, this particular range of X, is basically covered everywhere in the ERC. So one would say it's 100% coverage. And for Zeus in comparison, one can see a lot of white, which basically means there's no acceptance, and that would summarize in numbers to 2% versus 100%. So clearly there's a tremendous and huge gain in acceptance for forward tagging for these measurements. And here just on the left bottom here, I'm just showing how that's done. This is the forward region for the ERC as envisioned. There's a spectrometer. There's off momentum detectors for particles away from the beamline. There's other Roman pods for particles that are not bent as much, so basically inside the beam, and also the CDC, which is most important here because that's important for Pion structure functions to detect this neutron. You see the acceptance again across the board. It's very good. It's 100% as shown here in the numbers. Okay, so then let me move on a little bit. So this is basically not something that in the ERC and meson structure functions is not something that happened yesterday. That's something that's been ongoing for a couple of years now. It's basically based on workshops that started at Argo National Lab in 2017 and followed up by a follow-up at CU8 2018. Here you see the pictures here, the websites. And since then, we have continued having these workshops, some of them in collaboration with Amber at CERN, just again, because this topic of emergent hadron mass is, of course, across the board of interest to all facilities. And it's important, obviously, to make the measurements most complementary as possible. We also saw we have published 2 papers since kind of the first workshop. So the first paper was in 2019, then we followed this up in 2021. This was actually, the second paper was in the context of the ERC user group yellow report. So you see here some information about that. So at the moment, these are the current members of the working group. Also includes members, of course, from Berkeley. So we have about 27 members at the moment. There's sometimes students joining and leaving, of course. We have 18 different institutions, 10 countries. We meet every 2 to 3 weeks, and that's been going on for about well, almost 2 years now. If you want to join, you can contact me, or of course, we have here on the call, I think, John, Shuyu, or so, and so you can contact either of them. They will give you information, or I can give you information about it. It's a very successful, that's been a very successful effort before the Yellow Report, during the Yellow Report, and even after. And we believe we will likely continue existing and continue on with our studies. Indeed, the next meeting is this Thursday at 5 p.m. Eastern time. So if you'd like to join, just give us a note and we'll give you the Zoom instructions. Okay, so coming back to the physics here. So I already mentioned, basically what we're looking at is that we have two mass generating mechanisms. One we're mostly interested in is the one embedded in QCD, the strong interaction piece. Essentially, that's responsible for the emergent mass, or the emergence of this 1 GeV scale, if you like, that characterizes the mass scale of the proton. And so also all observable matter. And so then there was still some puzzles, some mysteries. So in particular with the masses of Pion and Kaon, where we said that sources and impacts of this emergent mass remain puzzling and should be definitely understood. So there's questions like, are there more or less gluons in the pion? If you look at the mass, is the pion empty or is it full of gluons? And EIC can contribute to this. In fact, it can contribute, as the first line here says, also for the proton, where it will allow the determination of an important term that contributes to the proton mass, and that's the QCD trace anomaly. So there, of course, I could say much more, but I will mostly here in this talk focus only on the Pion and Kaon, where the EIC will allow determination of the quark-gluon contributions with the Sullivan process, as I already discussed a little bit earlier. And of course, for much more information than I can cover today, you can refer to these references listed at the bottom. This origin of nuclear mass was already mentioned also in the Yellow Report. So in particular, again, I mentioned there were these two questions. One is, of course, related to the proton mass and the trace anomaly of the QCD energy momentum tensor. Again, I will not say too much about it. I will focus on the part that was in the Yellow Report that says to address the emergence of mass through the pions and kaons. So just again, just a very brief mentioning here of the theoretical background. So if you look at very specific limit in the chiral limit, using the parton model basis, then the entire proton mass would be due to the trace anomaly. So that would be this expectation value as you see here. And then if you do the same thing for the pion, one would, of course, see that the mass of the pion would be 0, would disappear, and so contributes basically nothing to the pion mass. Now, if you think about it, what I said, and I think it was the first or second slide, that seems unlikely because, of course, quarks and gluons still dynamically acquire mass. And it's a universal feature of hadrons. So it's more likely that this cancellation that's shown here is basically what leads really to 0 and gives the pion and kaon mass. However, from the experimental point, of course, the question that I would be interested in is just simply, I mean, are there actually gluons now at large Q squared in a pion or not? So then let me say a few words about the mass budgets, proton versus the pion and kaon. Here on the top, you see the proton mass budget. You see that the mass in the chiral limit is in blue here is very large, even in the absence of the Higgs boson. Well, the Higgs boson coupling, of course, into QCD. The non-zero part here, this is essentially in manifestation, if you like, an expression of the emergent hadron mass in the standard model. Now, if you look at the picture then of the pion and the kaon, you see essentially the mass in the chiral limit is well, 0, it's massless. And that owes owing also to the emergent hadron mass itself via the dynamical chiral symmetry breaking, which I discussed a little bit earlier. You can see that 95% of the pion mass is essentially due to the emergent hadron mass and the interference with the Higgs boson, essentially. Similarly for the kaon, here it's a little bit less due to the kaon, as I showed earlier, being kind of in between the emergent hadron mass and the Higgs mechanism. So the kaon clearly is a very good example of a system to study if one wants to see where the impact or the threshold is of the emergent hadron mass versus the Higgs mechanism. Very interesting here when I talk about opportunities through kaon and pion structure pion and kaon studies is that there is that we basically in the progress of the whole field we profit from the interactions and the formation of kind of tight links between the dynamics in the QCD gauge sector and the properties of the light front wave functions. I already mentioned it earlier. That's of course important here if you're talking about interpretation of probabilistic interpretation of pion and kaon structure. Here in particular, what's of interest is that in lattice QCD has already been able now with large momentum effective theory to deliver results on pseudoscalar distribution amplitudes and basically expose important features that one can on the lattice, of course, explore further. So here in particular, you see the pion and the kaon, pion on the left, the kaon on the right. You see as the pion mass decreases from about 700 to about 100 GeV, you see a quite a considerable change in the amplitude. So it goes from something that's somewhat asymptotic to something much broader as you reach essentially what I will say on the next slide is where the region where the emergent hadron mass mechanism is dominant versus the Higgs mechanism. And so basically by studying with a numerical method like the lattice QCD, one can get a handle on learning about the emergent mass mechanism. Now for the kaon, what is important here to point out is that this distribution is a little bit distorted with respect to where it should be centered at about 0.5. And that is also important because, as I said earlier, this exposes the Higgs modulation essentially of the emergent hadron mass. So again, the kaon itself is a very important particle system to study here if one wants to learn about these mysteries of the emergent mass sources and their impacts. So here, as promised here, I'm showing the emergent mass versus the Higgs mechanism, essentially summarized in this picture up on the top left. So again, we see the green curve, which is kind of broad and squat. We see this is the curve where the emergent mass is dominant. So one could say that's sort of what some people refer to as the real life wave function, if I like a distribution amplitude. Then we see here the curve B is a heavy quark system, the eta here. And this one is even narrower in distribution amplitude than the asymptotic form. And so basically shows that it is primarily dominated by the Higgs mass generation. And then, of course, in between, one would have the pion that's not shown here. Unfortunately, as said earlier, it would be, of course, nice if one could measure directly these functions. Of course, we know we cannot. And so we have to measure it through the observables, which, of course, we are fortunate that we can do it. We can measure the pion and kaon elastic form factors, which can be related to these distribution amplitudes. And we can also measure the structure functions. So again, this just as a kind of introduction. And here I'm showing again, I already mentioned it, so I'm not going to talk about this in more detail. It essentially just shows that depending on the degree of dynamical chiral symmetry breaking, so your distribution amplitude, you can calculate the pion form factor. It will be different depending on how much dynamical chiral symmetry breaking goes into the distribution amplitude, and can of course then be also verified experimentally by making these measurements. So instead, I will just say the prospects for making these measurements at EIC. So if you remember from earlier slides, what we wanted is to have an expanded range in Q squared to actually make and draw these conclusions on the distribution amplitudes. So here shown is the projection, making a couple of assumptions. Going back here on point 1 and 2, essentially, if you remember from before, what we needed to show is that we have a strong dominance of longitudinal cross-section because we need that to extract the form factor. We also need to verify that the solvent process works. And I also discussed this earlier, so we will also measure or have to measure to make this measurement this ratio of pion, charged pion negative to positive ratio to show if there's non-pole backgrounds and their size. The next assumptions are on the experimental facilities. So we have essentially here 5 GeV electrons on 100 GeV protons, certain luminosity. We have a model to extract. We assign a certain uncertainty for this to isolate the function is isolating and extracting the form factor. And this is what we get. So here's the projections for the GeLab 12 GeV. They end at about 10, as I discussed earlier. And then EIC finally will be able to extend this as required to a range of about 40 GeV. So this is great. Next question, of course, would be, can we do the same with the kaon? Well, this is something that's still being worked on with our group, essentially. We have to would have to somehow make LT separations. We would need to emphasize lower energies. It's not entirely clear. We need still guidance from the experiment that luckily we took data about 2-3 years ago, which could give us this guidance to how to make these measurements also possible at the ESC. Coming to the Sullivan process for the PION and KAON structure functions, here I show the same picture as before. So we're talking here about detecting the scattered electron. We don't detect the PION KAON target. We do detect a tagged neutron lambda going very forward. I'll say a little bit about this, and that's where the ESC has a major strength, of course, for the acceptance for these particles. And this is where it is. So I'm showing you here kind of a, if you like an introduction to the ESC detector and its nomenclature. So if you're talking about the scattered lepton, that's in this plane here. This is also where we would detect the electrons from the PION and KAON structure function measurements. So it's quite standard to detect these particles. Here's just shown how they show up in basically polar angle and in momentum. So it's nothing out of the ordinary. So this is quite well understood. And here is what I was mentioning many times. This is really the distinguishing feature: is the leading baryon that needs to be detected. It goes at very small forward angles. You see it here. It's about 1 degree, maybe up to 2. And is nearly at the beam momentum. So very energetic and very small angle particles to be detected. And to do this, again, you recognize this plot. I showed it earlier. We need this whole system of detectors in the far forward region of the ESC. Particular for the PION neutron detection, we need energies, as you see here, 5 and 41, 5 and 100, and so on. The CDC has to have a certain size. I didn't discuss it here today, but there's more studies you can find in the literature that we published. We need a detection efficiency 100% with the CDC, as also as discussed already. And there are some details about the K lambda in particular, this detection, because of course the lambda is decaying. So there's some additional details one has to take into account, and they're listed down here in terms of the decay channels and what detectors would be needed to do that. The other point, as I already mentioned, standard electron detection, but we would need good calorimetry, hadron calorimetry for the delta X resolution, in particular at large X. And I don't want to say too much. I think here I just want to mention, compared to Hera, why should these measurements be possible at ESC? Well, the luminosity, as you see here, it's a factor of 1,000 higher than at Hera. The detection fraction is much higher at Hera. The fraction of the proton function illustrated here, you see it on the vertical. The PION versus proton structure function is about 10 to the -3. So basically what we're measuring is the PION structure function. So we are in good, we can be confident of that. And so the data that we expect at the ESC for the PION should be comparable or even better than the proton data at Hera and the 3D nucleon structure data at COMPASS. However, of course, it depends on this last point that we convince ourselves, or we can convince ourselves, that we can map these PION structures, in particular for these T regions, if the Sullivan process can be validated. And if we can do this, then we would gain at least a decade compared to Hera and COMPASS. So it looks very promising for sure for ESC. Just very briefly, where we would come in with ESC, this is the plot I showed earlier, just showing again the data from Hera, where they end about 10 to the -2, 10 to the -3. So basically constraining the data at low X. If you then go here in PION structure function and look at these arrows, that's where the ESC would come in. So you see that nicely connect to the Hera data and extend into the moderate or intermediate to larger X regime. And looking in a little bit more detail, so you see again here different Q-squared panels for as a function of X, the PION structure function versus X essentially. And you see that in green, the uncertainties look quite promising for making such a measurement of the PION structure functions at ESC. And here, as a function of T, same plot PION structure function as function of T, and highlighting the value of T in which up to which we want to measure and around which we want to measure to basically show and validate and illustrate that the Sullivan process is the dominant mechanism, and yeah, basically to be able to extract this structure function and verify the robustness of the interpretation, as it says here. So it looks very promising. Also here in green again is the uncertainties for the kinematic regimes where the ESC will provide data. So good prospects. Then in terms of interpretation, shown here is an example from the yellow report, where the data were combined with existing world data. So that would be the data from Hera and from also the Julian data from Fermilab and CERN, and extracting the distribution functions, as you see here for glucy and valence. And you see certainly that plus ESC, that there's a certain impact, certainly quite an impact for these measurements and extracted PDFs from that. Also, if you look at the moments, that's of interest, of course, because that's something we can then relate also to the lattice QCD and so on. We can also see a rather big impact of the ESC data in both one or three, in fact, of glucy and valence quark distributions. So again, it looks very good moving forward, and ESC should be able to provide us with a lot of information on basically shedding light on this puzzle of the source and impact of the emergent hadron mass. For the kaon, I guess I'm not saying too much because I'm running out of time here. I'm just saying that ESC projection again suggests that we should have a good measure, a good data set here of determining or addressing the question if there's less glue in the kaon than in the pion. And here are the reasons, of course, why that would be the case. But I'm not going to say too much about this, and just refer you here to the projections with ESC and the impressive uncertainties that we expect. Just ending here with all the questions we have been publishing and we have been treating also in the meson structure function working group. You see here the science questions that we are addressing. They, of course, I mean, global science questions. So, so one can, of course, have to take this with a grain of salt, that one has to probably phrase them in theory much more carefully. But this is overall the question. So if there's quark-gluon energy contribution to pion mass, we talked about pion structure function data over a range in x and q squared. That's something that the ESC will provide. I talked about the question here to get a quantitative guidance on the emergent pion mass mechanism. And that would be done through the pion form factor measurements at the ESC. And I mentioned the range between 10 and 40 GeV in q squared at ESC. I also mentioned, of course, in terms of comparing now to the Higgs mass mechanism, so what is the size and range of interference of the emergent mass in the Higgs mechanisms? Well, the kaon form factor data possibly that can be taken at the ESC would be shed a lot of light on that. As I mentioned, that's something that's still ongoing in our meson structure working groups, has to be studied and checked if that measurement is actually possible. And there are various other measurements, as you see down here, that also we are investigating, and that have been some initial projections have been published in our publications from last year. Then, of course, there are a couple of more speculative observables, as you see here. So what is the trace anomaly contribution to the pion mass? If we can obtain tomographic snapshots of the pion in the transverse plane, so basically measuring pion GPD, and also all the transverse momentum distributions universal in pions and protons. So these questions, of course, are also being investigated, some a little bit more than others. In fact, there's a lot of also activity on DVCS of the pion target going on from our theory colleagues in the group. And of course, we're looking always forward to having some exciting new results this year. And so I will summarize here at this moment. I think I guess really running out of time. So let me summarize. So I hope I was able to convey here to you today that in my mind, protons, neutrons, pions, and kaons are main building blocks of matter. And I would say if you really want to claim that we understand hadron structure as relevant for the visible world, I think we have to understand at least the pion, kaon, proton, neutron, and likely also the lambda at the same level. Interestingly enough, we have the biggest opportunities with the lightest pseudoscalar mesons. They appear to be the key to our further understanding of the emergent mass mechanisms. And these mesons in particular are namely the pion and kaon, which we also know as the Nambu Goldstone modes of QCD. Very importantly is this last point, because we have these opportunities, or we are profiting in our progress from the strong links and the formation of these links between the different aspects of phenomenology, the continuum QCD-based approaches, lattice QCD, and the global analysis of particle distributions. All of them play a role and are interconnected and are needed for making the progress here. And all of them overall, of course, are also linked to the experimental measurements. And here I mentioned that we have this unique opportunity that we have a whole array of experimental facilities being upgraded, coming online, and so on in the next decade or so. So it's a really exciting time for meson structure. Just to orient you and give you the summary here of Jefferson Lab, EIC, and so on. So I mentioned to you that Jefferson Lab will provide at a center of mass energy of 5 GeV already quite interesting data for pion and kaon. This will go up to form factors of about q squared of 10, as you see here, or 5 for the kaon. And also make measurements of the pion kaon structure function. So also have a large impact, as you see down here. all through the solvent process. And of course, also importantly, I pointed out, also through for the kaon, which is the first data of its kind. There's been no kaon structure function data available so far. So that's Jefferson Lab. Then the unique role of the ESC will then be to access the PION and KAON structure over a very large range in center of mass energies. It's impressively large, 20 to 140 GeV. And with this large center of mass energy, one can say that the ESC will have the final word on the contributions of gluons in pions and kaons as compared to protons, and settle then the questions that I discussed earlier: how many gluons persist as viewed with the highest resolution in this vastly extended range in Q squared in X, and chart essentially the pion and kaon structure and our meson structure knowledge. And again, here's the summary of the pion structure measurements and the meson form factor as we reviewed today. And then my very final notes here, I just like to say that, again, meson structure measurements play an important role in our understanding of the structure and interactions of hadrons based on the principles of QCD. These can be accessed through the meson form factors, which can be accessed through the solvent process. The technique here has been validated experimentally, and I've shown you examples of this from the Jefferson Lab. And have shown you in particular also the prospects of extractions up to the Q squared of about 10 or 6 GeV that are coming up in the next few years. Then I also talked about the opportunities to map meson structure functions through the solvent process, in particular through the GeLab TAG-DS experiments that aim to resolve the large X issues. And then finished up here the discussion with the ESC and the prospects of mapping the PION and KAON structure functions over a very large X and Q squared landscape, and possibly giving the final word on the impact and the role of gluons in pions and kaons and protons. And that's it. So thank you very much for listening here today, and I'm happy to take any questions.
Excellent. Tanja, thank you very much.
I cannot see, I think, people, but...
We have time for questions. Fong, please.
Yeah, thank you very much for the interesting talk. I just have some general comments and maybe some questions. So I think it's very nice and also interesting to really study the process you mentioned for pion form factor, has a meson form factor, and meson structure function. I think that's very interesting and also important subject. But I think it's kind of too much stretch to really connect that to the mass of the pions or emergent mass mechanism or something like that. I just have counter argument say that we know the proton structure function, proton distribution well. Actually, I mean, from the measurement from HERA and also GeLab and so on. So do we really understand proton mass, right? Origin of the proton mass? No, actually not, right? We still try to understand how the proton mass come. So I think that part is too much stretch, but the physics itself, it's very interesting and important to understand. And you may argue that in this certain model, so-called continuous QCD approach or Dyson Schringer approach, you do have different mechanisms to generate the mass. But for that, it's really based on model. I can say same for the proton structure function. We have back model. Back model certainly have certain contributions, certain terms. Do we really study for example, by constant by studying proton distribution? No, you don't, because that's a model. So some of the model dependent statement, that's fine. But if you really stretch too much on the mass generation, that's kind of too much. So I have a question. I think it's very interesting that GeLab measurement can really help to pin down the largest proton distribution for the pion. My question is that because really you do need precision for that measurement. And we know that for the GeM process, there's a certain things you have to take into account. You mentioned that high order correction and the resummation effects and so on. And here, of course, the precision required, you really understand the solvent process. That means, for example, the finite T correction will not mess up your measurement for the proton distribution. So I hope you can kind of give us some kind of confidence that you do understand the physics in that region at the large X, because the cross section is very small. So you have to be able to really give a accurate measurement for that.
Right, right. Yeah, thank you for these comments. I think they're, like you said, they're very important. I think what I would say is for the meson structure, I think I would not disregard it, because I think you need basically to understand all systems, particularly if we're talking about, like you said, I mean, I don't want to say that I think I want to just go back, or step all the way back and say that I think we probably agree that there's a dynamical scale, and that's probably I think independent of any model at the moment that I would say. I don't want to specify any model essentially. I think I would just say that depending then on how you, in particular, if you're talking about decomposition of the mass, which I mean, you kind of sort of refer to a little bit, I think the challenge is really to make the connection to the observables that you can get to with some sort of controlled approximations, which are essentially PDFs that you also refer to. And certainly, I mean, like you said, I mean, the proton plays a major role in all of this. I just wouldn't disregard necessarily, for me at least, the pion and the kaon, because it seems to me that they can shed additional light also on the proton itself. So I think, to me, you have to understand all systems to really understand this whole problem of understanding the light hadron masses. So that's my comment on this one. So I don't, like I said, I don't want to necessarily say or highlight or emphasize one model over the other. To me, I'm an experimentalist. I just want to provide the observable that might then be used to address this puzzle. But then let me come to the second part. You said about the measurement. Yeah, certainly that point is well taken. And I think we have shown with the form factors that we have studied very carefully the applicability of the Sullivan process. The same we can, of course, do also with the structure function. So I kind of showed to you, like, we would measure as a function of t and then compare with the phenomenological expectation with theoretical prediction, if you like, and basically make sure that we can really extract this quantity similar to what we do with the form factor. But the point is well taken, that we really have to study this carefully to make sure that we can be confident what we're extracting. So yeah, thank you again for these comments.
Yeah. Just add an additional point that really concern the higher order corrections. For example, resummation effect you mentioned in your presentation by Warner, my friend, and his collaborator.
Yeah.
So the spatial resummation factor will be different compared to and the DS. So I think this will be one important point if we can really get precision. So the precision is really the key. So I think my question basically try to kind of say if the Sullivan process really understood, because if there's some uncertainty from the approximation you take in this Sullivan process, that will ruin everything, right?
Right. Absolutely, absolutely. Yeah. No, this again, we definitely understand that point. And once we take the data, that would be interesting, because then we can really analyze and figure out what's possible. I mean, the projections you saw, of course, we have taken into account some of these possible uncertainties, but only the data will tell. I mean, data will be the data that will really tell us. So that will be exciting. These experiments we expect to run in the next few years. So yeah, stay tuned for that.
Okay, looking forward to that.
Perfect.
Tanja, I had a question back on your slide 11, when you were separating out
all the way back.
Back, exactly. You were separating out the longitudinal cross-section and the transverse cross-section. Tanja, probably this is a very obvious question. Close? Yes, exactly. Would you tell me something, these cross terms, how do you get them to go away? Do you tweak phi? What do you do?
One could do that. Yeah, one could do that and average over the azimuthal angle, then they would essentially go away. In this case, we're basically just fitting and extracting them directly. We're taking data. It's actually an interesting question, because to take these data, I mean, technically, when you just take data all around phi, you kind of never have access to these terms. But we take data in a way kind of off the virtual photon direction, so we can actually also measure these terms in addition to the other two. So we have a good handle on the size of them. But yeah, that's a very excellent question.
Thank you.
Because they are pretty small to measure.
Very nice. And then, Tanja, so my last question would be on slide 20. There's some, there was the constraints on the kind of meson that the neutron is exchanging. I think it was the isovector
Oh, this was probably going back.
20.
ISO.
I
Oh,
thought,
20, okay.
I thought it was
20.
20.
This one? Mhm.
Yes, in purple at the bottom, neutron events, isovector. Would you tell me physically what's going on? The neutron only exchanges which kind of particle?
Yeah, so in this case, the main thing was simply to say that I mean there's studies, many studies that are being done essentially, but you can identify a pure isovector exchange, which is kind of shown here. Leading proton should be 1/2 a leading neutron. The data show something a little bit different, so it just shows additional isoscalar exchanges for the leading proton from that. And from this, one can then conclude that the isoscalar events also include the diffractive scattering, so that the neutral pion is basically, yeah, it's buried. It's not of interest here. And so you have only isovector neutron events that contribute, which would imply that you have the charged pion process, the charged pion being the dominant process. And so that's what tells you that essentially the one pion exchange, which is basically the pole diagram that I talked about earlier, is the dominant mechanism. So it's one way to address the question that Fang was also asking about, how to verify that this pole process is actually dominant.
And that's not surprising. That's sort of expected, correct?
Yeah, that's right. But there will be different ways. I mean, as I also said for the meson form factor, different ways that we will look at this to really make sure that the solvent process is the dominant one, because that's kind of the first question or the major question to address experimentally, to make sure that we can actually extract, like it says here, okay, we have some sort of basis to say that we're confident we can actually extract the quantity, in this case, the pion structure function from the data. So that's a lot of the experimental program is about these validations, as I showed for the meson form factor earlier, and then here also for the structure functions.
Very nice, thank you. Okay, so if there are no more questions, we will thank Tanja again very much for talking with us today, and see you all next week.
Thank you, everyone.
Thank you so much for being here.
Bye.
Bye.
Bye-bye. Thank you. Bye. Take care.
Bye.